Hello, Vincent, my friend.
Hello, Sergey.
What have you been up to? Been reading archive lately?
Yeah, I have actually.
Me too. Yeah, so we decided to do this spontaneous live read on the new paper, right, by Microsoft Quantum, which appeared last night, and we had a look, and we will go through it. And we welcome questions if you have any, if you manage to find time to connect to this spontaneous event. So let's go.
Yep.
So Vincent, have you studied the paper?
Yeah, I actually managed to have pretty decent read of it. Shallow, of course, quick, but full read. What about you?
I carefully studied the whole paper, of course. I'm a tenured professor, right? So I looked at the figures, the references, etc. No, I actually also had a careful look, but still, we have to say that this is a live read, and it may not be final, but we are fairly confident we can review. So let me share my screen, and we can start looking at the paper. Yeah. So it's archive 2207.02472. The title is Indium Arsenide Aluminum Hybrid Devices Passing the Topological Gap Protocol. Pretty nice title.
Yeah. So doesn't say Majorana in the title.
Yeah, they avoid the M word, but still it's pretty decisive, and
yep.
Yeah. You can also, of course, we should say that kind of been expecting this paper because there was a press release that Microsoft made that made quite some waves back in March. During the March meeting, we had a lot of discussions with people about it, and the title of the press release, which is March 14, is also very decisive. So Microsoft demonstrated the underlying physics required to create a new kind of qubit. So you can go back to that release and scroll through it. There's a nice video with a fireside, by the fireside of the two principals of this work discussing it. And there is some nice modeling. There was no data though at the time, right? So have you seen any data until last night?
So one thing, I really think this is the paper backing up this announcement, because at a first glance, I think some of the numbers, etc., quoted in the blog post correspond also to in the paper, and the storyline really fits. So I think we can view this as the scientific underpinning of that announcement in March.
So the devices passing the topological gap protocol are really Microsoft demonstrating the underlying physics that will enable new types of qubits. That's what we can conclude from the putting 2 and 2 together from March and July. Okay.
And perhaps if anybody with a generic quantum information computing background listens to this or is attending, there's no qubits in this paper, no Rabi oscillations, no T2s, etc. It's a claim about the underlying physics.
Yes, so the qubits are still some ways ahead, I guess. Okay, authors of the paper are listed as Microsoft Quantum. That's a little unusual for our field. I suppose that's because it's a really large collaboration. You have to actually scroll all the way through the paper. Even my computer is not handling this PDF very well. And at the end of the paper, you can see the names of all the authors, somewhere here. Here they are. So corresponding author Chetan Nayak, and then here is the list of all the authors. That's getting towards the particle physics scale of the size of the collaboration, right? Very large collaboration, and you see a lot of familiar names on this list. Also a lot of new names. One interesting thing I see is that we have experimentalists located in different parts of the world, like different countries in Europe and Australia and United States and so on. So do you think they all came together to do these measurements, and they collaborated in some other way, perhaps?
Yeah, so I think a lot of these people are probably also still university co-affiliated. I doubt this is solely Microsoft affiliated, but you know, it's hard to not 100% sure, but I suspect so. And I do think that probably this work was carried out in probably various places in at least 2 labs, I suspect, in Delft and Copenhagen. The experimental work, the theoretical work, probably took place, you know, delocalized in a sense. But
so
probably
do you think they cooled down the same device in different places? Because usually there is a dilution refrigerator in which there is a sample and measurement computer right next.
So it's hard to be certain, and this is something that would be interesting to hear at some stage, where the experiment was actually carried out, but I wouldn't be surprised. Maybe it was parallelized. It looks like a fairly extensive experiment in a way. So I can imagine that it happened in multiple labs. Also possible that it's also a possibility that it just happened in a single lab. It's hard to say. My gut feeling is that it was probably a joint effort spread a little bit in like the 2 experimental labs, I suspect, which to the best of my knowledge are Delft and Copenhagen.
This would be an optimistic read of this. Another thing I notice here is I know some of the people who grow semiconductors, and I can see on the same paper people that specialize in 2D structures, quantum wells, and nanowires at different locations, again, all on the same paper. So that would seem to suggest that maybe materials were contributed by several different sources, if all these people are present on the paper. Really hard to say, because there is no author contribution section in this paper, right? Not only the university affiliations that some of these people have are not mentioned, but also the author contributions are not stated. Some of these, I believe, are actually Microsoft executives. Some of these names are not experimental or theoretical physicists related to the sort of the demonstration of the underlying physics, right? So I guess that those people have also done some kind of meaningful contribution to be listed as authors here. Also
In any
interesting.
case, we thought it's
okay, yeah, go ahead.
I was just wanting to say we thought it was worth dwelling on it because I think it's somewhat unusual in the field. It's something we might start seeing more and more often as collaborations grow and grow. But this is still fairly fundamental research, and we're more used to a format where it's a regular university-sized team or a few collaborative teams, etc. But this choice has not been made here. It might happen in the final publication.
Yeah, so I also noticed that a couple of people, to my surprise, were not listed as co-authors. It's easy to figure out who they are, but basically the biggest scientists on the 2 teams, Leo Kouwenhoven and Charlie Marcus, are actually not the authors on this paper. That's very interesting, because I think intellectually you can trace a lot of this work to them, and they were there until recently anyways. Okay, let's dive in, I guess. So this is sort of journal club style, right? A couple of guys looking at the paper, trying to figure out what it says. So perhaps let's look at what the device is and what they're trying to measure here. Maybe this figure 2, is a useful one to look at. So what do we see here?
So it's not the simplest possible device. It's becoming somewhat the simplest possible devices in this type of research is a 2-terminal device with which is sort of like a fancy transistor with with superconductor in there and a semiconductor, etc., gates to control it. This is a little bit more advanced. It's a multi-terminal device. So let me quickly see.
But still, at the center of it is the same element that
yes, this is the
many people study, right? The semiconductor wire, which is here in the middle, the dark line, and it's covered by a superconductor. So it's got to be somewhere here, or in this SEM picture, or at least an optical picture. It's somewhere here in the middle.
Yep. Yeah. So it's the classic implementation of the one-dimensional wire proposal that people have been pursuing since 2010. First proposed in 2010. All right. What else? So there's not many details on the barely any details on the fabrication protocol. This is so in that sense, I think the paper is simply incomplete. It would be impossible to reproduce this device based on the paper alone. So we are not exactly sure what type of how the material was grown or how the device was made. It does appear that it originates from a 2-dimensional material and that somehow a 1-dimensional structure was made out of that. And that is, I think, somewhat obvious when reading through the paper and through the figures. And the fact that there is an absence of fabrication protocols throughout the paper is, I think, again, somewhat unusual and a break with all the work hitherto.
So if we look at panel D, I guess we can find some confirmation of what you're saying. The blue layer in panel D is an indium arsenide layer, which is everywhere, and then on top you have the yellow, that's metallic gates, which corresponds to this yellow here. However, the superconductor aluminum is a very narrow strip, so it must have been removed. It must have been a layer everywhere, and then it got etched. So the device underwent chemical processing, etching, also thermal processing, because there's a dielectric on top, and usually that involves heating. So it could have been a pristine structure that was grown in some fancy molecular beam epitaxy machine, but then it received quite a bit of processing afterwards to create a very narrow and very long nanowire. Another thing I noticed, you say not many details are given about how the device was made. What I see is that also the scale bar is missing from the figure, so we don't really know how long the wire is. We can guess it's many microns. But here panel B or panel A don't have any scale on it. So the wire must be quite long, but we don't know exactly how long.
Yeah, I might say in the text here or there, they might give a number for how long the section between the center section, how long it is.
So wire is partially defined by gates, by negative voltages on these gates, but it is also defined by etching because superconductor has been actually etched. Now, what about these probes? What do the probes do? So we have voltage left, voltage right, and current left, current right.
Yeah, so these are basically used to apply a potential and monitor the current flowing through these terminals. And I think the rest of the device is grounded. So in the center and on the left and on the right, there's a connection. Let me think about the center. Is the center directly grounded?
No, I think actually there is only ground on the left and on the right.
Left and right, yes. So it's not a float. So it's ground on the left and on the right, and then the two terminals are used to apply a bias voltage and monitor the current. Yes. So that's basically that you can measure transport through the device. What else? There's some gates to define the structure, and actually on the, let me see if I can.
Yeah, so the
here,
idea, the vision behind this device is panel C, right? The blue trace above, this noisy trace, that's the topological Majorana wave function, which would live all across the wire and peak on the left and on the right sides of the device. And this entire orange region in between would be the topological region where the topological gap, which they're trying to investigate and apply the topological gap protocol to find, would be located.
And then here where I put the arrow on the left and also on the right and also here on the left, that is where you sort of using a gate, you cut the device off. So you induce a potential barrier and then you make sure that there is a tiny bit of transport possible that you can do tunneling spectroscopy.
Yep.
Yeah.
Exactly. Okay. So what is this topological gap protocol that they're trying to apply? Can we explain it using this measurement? Maybe we can do it using this figure. This figure here, figure 4. You see it?
Yes. Yeah. So basically, it from an experimental viewpoint, I think it consists of 3 different measurements. Two of them are given in the top panel, in panel A. So that is this measurement here on the left side, and there is the same measurement on the right side. And what the protocol is quite simple. You start looking in parameter space as a function of the gates and an external magnetic field, and you look for 0 bias peaks to show up. And specifically, you look for 0 bias peaks to on either end, so either on the left or on the right, but then you look for regimes where they coincide. So you're searching for 2 0 bias peaks, one at either end. And then the idea is that once you have found that, you check if in those regions where you see the 0 bias peaks, if you also can find in this non-local measurement where you measure from the one terminal to the other, which is depicted in panel B, you measure if you see a little gap in the spectrum.
Yeah, so the idea of panel B is that they say that they try to send a signal through the entire wire. There are different ways to do that. It could be a kind of a non-local signal, meaning the signal is grounded on the right, but some signal gets to the left side. But the idea is that if the signal gets all the way across the wire, it must be due to quantum states that go through the entire wire. And so if there is quantum states everywhere at any energy, means there's no gap. So if there's signal at all energies, means there is no gap inside the wire. Now, if there is an interval where there's no signal in a non-local, means there is a gap. And so they try to correlate this signal, the non-local signal, with the local signals where they want to see the 0 bias peaks. And here, coincidentally, we just finished the review of a related paper, which we think is the underpinning of this method, which is this physical review B paper, closing of the induced gap in a hybrid superconductor semiconductor nanowire. So this is from last year, and some of the co-authors coincide, which is not difficult when you have 100 co-authors. But we think it's the key co-authors that introduce this technique. And in this paper, well, they do the non-local measurement, and they claim that they see the gap and they see the gap closing. They don't see the gap opening again, which would be topological, right? And if you're interested, and we think it's important, then you should go to PubPeer or to my Twitter, and you can read our opinion of this paper. Basically, we criticize whether this technique is really capable of identifying a bulk gap, so a gap of the states that extend through the entire multi-micron nanowire, like 1, 2, 3, 10 micron wire. And we think it's due to a lot of different disordered regions where localized wave functions are present, not really any bulk to talk about. So this is the review. And for completeness, I also want to show this theory paper from last year, which the Microsoft authors themselves say that this is where they conceptualize the protocol, the topological gap protocol that they have now applied to some experimental data. So it looks like the theorists came up with the protocol and now applied it to some data.
Well, there's actually some experimental people on the author list as well. So there's probably, a theory protocol heavily informed by experimental reality, going back and forth with people in the lab, I suspect.
Fair enough. So yeah. What do you think about so they say the quality of the structures is very high, mobility exceeding 60,000. Here is the 60,000 number. I have it on the screen here.
Yeah. So yeah, a couple of comments.
100,000.
Yeah, so a couple of comments in the supplementary figure that they show at the end of the paper. They do a mobility fit, which results in 60,000, so the lower end of that range. That measurement is done in a Hall bar, apparently on the same structure near the device. So this is a fairly typical standard measurement to measure mobility of a two-dimensional system, but I think it is important that we are seeing a device here and data from a effectively one-dimensional structure. And why does that matter? Because it did involve a fair bit of processing to go from a large, de facto two-dimensional slab of material to shape that into a one-dimensional wire. And this is, of course, widely known that whenever you do fab, you induce disorder. So I do not think that these wires have the same mobility as the 2DAC. It is probably lower. What this number is, it's not been studied in the paper. Would be very interesting to see basic measurements on that. I suspect it's actually a fair bit lower than the 60,000 shown for the two-dimensional material.
Yeah, in my experience from my research, it could be quite a bit lower, like 2 orders of magnitude lower, like 1,000 or so. And here I'm a little bit disappointed that we are only given this very low resolution picture of the device. There I zoomed it into the maximum and where I can see the pixels, but I hardly see the nanowire. So it looks pretty from the zoomed out point of view. When I try to see what is actually inside that wire, I can't. And the reason I want to see that is because, still the structure has been etched to remove aluminum, and the etch is typically rough. The edge has a certain roughness. Even small roughness is quite detrimental for Majorana. The structure has been processed thermally, and what that does to aluminum, the superconductor, is it can form grains, and each grain can have its own gap, and we just don't see how the device looks, right? And we cannot assess that, but based on all and every single prior experiment, to create a multi-micron wire, like a 3-micron wire, 10-micron wire, even a 1-micron wire, without disorder at a perfect scale with no grains, no roughness, such that there's no localization due to, let's say, trivial Andreev states, has not been achieved so far. So there are two options. Either all these non-ideal effects are present in the Microsoft device right now, but we cannot see that from the picture, or they have really made a ginormous leap forward with device fabrication, which is not disclosed in the paper. Those are the two options.
Yeah, and this is really, in my opinion, this is a crucial aspect, that if, let's be positive, if they manage to make such a fantastic device, this is a legitimate result in its own right to thoroughly prove that and demonstrate that, I would argue.
Yes,
and we need that sort of verification and demonstration, I would argue, because this is, there's just nothing here really to verify device quality. No fabrication details, either process description or images, nor transport data, demonstrating or pointing in this direction.
Not be inclined to believe it until I see it, but also having peeked at the data already, I can tell you that I believe there has not been a breakthrough in fabrication achieved, to be honest with you, because I see a lot of trivial states in the data. But let's look at the results. So here's a nice picture. So it actually looks quite nice. This is what we call conventionally a phase diagram plot. So the phase diagram is in the space of magnetic field on the horizontal axis and electric field or gate voltage on the vertical axis, or in a theoretical sense, it's a chemical potential on the vertical axis, a gate voltage, and Zeeman splitting on the horizontal axis. And what you expect to see is the kind of a parabola shape that is lying on its side, parabola on the side, this kind of shape that I can see here very well, filled with signal. What this signal is zero bias peaks. And what is nice about this data is that we can see a parabola shaped signal on the left, and we can see the same signal on the right, right? So in the local measurements on the left and on the right, we see exact same shape that looks like a topological phase diagram. So this would be definitely a region that I would explore very carefully to find additional evidence of Majorana. And then finally, panel C is a joint. I think what this means is if you see a zero bias peak on the left, so in panel A, and on the right, so in panel B, then there is a bright signal in C. And so you can see that this parabola shape, interrupted by some non-idealities, that's okay. It is really present on the left and on the right. So this is quite nice.
Yeah, but this is all a simulation, eh?
Yes.
Just for clarity. Yes. This is simulated data.
Yes.
And
yes.
This is a general comment about this paper. It is a very lengthy paper. I think it gives a quite, okay pedagogical introduction to the whole system and to the theoretical model, but it is really theory heavy, I would argue.
Well, the corresponding author is a theorist.
Yeah. So you see that back in the build-up of the paper. It's pages and pages of model description and simulation results. So it's been commented in the chat as well. This is simulated data.
Yes, indeed. So this is a simulated data. And of course, when you plot simulated data, you have an advantage that you can simulate a topological wire. You can put the Majorana into the wire, and then you can see how it's going to look, right? And then, of course, you have something that we can buy, in a sense, right? There's something that looks sort of plausible and looks looks kind of as expected. So we can also look at the experimental data. Shall we do that? Or
Well, perhaps one more comment I want to make on this model. Also, in the if you watch the video back in March, this model is being heralded as a huge achievement. Like, and in a sense, it is. I think it is a really complex model, and many factors are taken into account. My immediate concern is that it's an extremely fine-tuned model. There's many knobs.
yeah, was it 35 parameters or 25?
Yeah, some number like that. There was a 30 in there or so.
Yeah, Microsoft people presented it as a strong point of the model.
I personally think that I view it more as a weakness of the whole modeling approach and the protocol in its own right, because what it will allow is fine-tuning of your model and your protocol to an extreme extent, to a point that you might find tiny bits and pieces of a topological phase in your model that you can then of course always, after a lot of fine-tuning and experiment, also match to the experiment. So this is a fundamental deep concern that I have about the modeling and the protocol.
Another comment I can make about the model, even in the model, right? So if we look at the coincidence plot, which is this panel C, right? I was focusing on this parabola looking region and saying, okay, yes, if I see that, then I can go along and think further whether it could be Majorana. But look, there are coincidences even in the model that don't look like that shape at all. Like, for instance, these elongated lines, random spots, more lines here. And those are don't appear to be topological. There appear to be some state crossing zero bias along a contour, but not filling a void in a space, in a phase diagram, which would be the topological region. And however, even in a simulation, these states are present, and they even give positives in this correlation plot. Although I should say this is not the full protocol, right? This is not the non-local signal is not included here. This is only local signals. So we will see more of that later. Okay. Right. So here is the analogous, real data, experimental ZBP, which is zero bias peak, ZBP. So this is just looking at a zero voltage on the both ends and looking, slightly oscillating it to pass a little bit of current, and looking around zero to see if there is any peaked conductance. So what do we think about this data? Do we buy it?
Look, look, this data is what it is. You see certain regions in phase space with zero bias peaks, experimental phase space on either side of the device. This is no surprise. This we know for a decade now, right? That you get zero bias peaks in these devices at finite magnetic field. We also know that this can happen on either side of the device, and that this can overlap.
Right. We had a paper last year also about this, right?
Yeah. Yeah. Look, Sergey, I measured this in my PhD already with Koen 6 years ago, right? Like, we know this happens. This means nothing to me because it's just it is what it is. It is a coincidence of a zero bias peak on either end. Nothing more, nothing less, and it doesn't say anything about the underlying cause, I would argue.
Okay, but I think the data is still. There is a lot to unpack here, so to say. It's quite revealing on several aspects. First of all, you do see the kind of parabolic shapes passing through. So here on the right, I'm pointing out one, another one. On the left, there's all these parabolas stacked on top of each other here. Yeah, those look in their shape like the topological regions. And like I already mentioned, when we looked at the theory plot, these are hollow, so we only see the orange contours, and inside it's bright white. And that's what you expect from trivial Andreev bound states, which were also first studied, let's say 8 years ago, 2013, 2014. So the boundary is along this line cut, this parabolic boundary. There is a zero bias peak, but then if you move in gate or if you move in field, then for most cuts, it crosses through and splits. It doesn't stick around. And we want it to stick around in a kind of an area to talk about a topological regime, maybe stick near zero, but not just disperse. And so what this boundary designates is a quantum phase transition boundary, but of a different kind, in a kind of a quantum dot. So with single particles, not a bulk nanowire. In a small region of the wire, you have a quantum phase transition between the ground state of spin singlet and spin doublet for the ground state of the Andreev bound states that are trivial, not accompanied by another one on the other side of the wire. This we also see here, right? For most of these parabolas, we see it on one side, like we see it on the left, and on the right here, you see my mouse? There is nothing. So it's only on one side. There is one on the left, there is one on the right. Now, there is some exceptions to this. Obviously, there is some coincidences, right? So there's 3 regions here in the overlap of the zero bias peaks. They really look like they're at the intersection, at the crossing of what we see on the left and what we see on the right, right? In the theory plot, we saw the same parabola on the left and on the right. In the experimental plot, we see sort of 2 things going through each other, and at the overlap, we have some zero bias peaks that are on both sides, right? That's what Vincent said about coincidence. And then there is a slightly bigger region on the left. So I guess it could be scrutinized a little more, and this is what they do indeed in the paper. Anything else?
No, I think we covered this enough.
Oh, well, I do have one more point to make then. If you don't want to make it, but it's about the gate scale, right?
Oh, yeah. Sorry. Yeah, I thought of it but you were talking so much that I forgot about it again.
Sorry. I
Yeah. So this gate voltage range is tiny. It's tiny. Given that they are applying voltages of the order of volts in absolute sense, I don't think they have disclosed basic data of the pinch-off, etc. So you don't really know how fast the device turns on and off, etc. But realistically, this happens. Should also be of the order of tens, hundreds of millivolts, if not volts. My point being that I suspect that this is a tiny little wiggling in the gate, probably fairly deep in the tunneling regime of either junction, meaning that these features that you see dispersing as a function of gate voltage, they disperse very, very rapidly. Typically, yeah, I would say that this is a little bit of a red flag to me, that in the sense that I would associate this with disordered systems, honestly. So many rapid fluctuations.
So you're making a point that in such a small gate range, just 30 millivolts on the gate, in the entire diagram, we have so many states, so many of these parabolas that it is, indicative of some rapidly changing landscape here. Yeah, but just from the basic experimental point of view, the entire region of interest, which is this part here, is contained within like 2 millivolts on the gate. Really, this overlapping region is so tiny. If my student brought me a region that is, they have to change the gate by 2 millivolts, I would say, okay, no, this is pathological. We're zooming in too much. I also was amazed by this line here. Do you see what I'm highlighting here? The number. Well, this is not millivolts. This is in the microvolts. This is with the accuracy of 10 microvolts, we are given a gate setting number. So, you know, for an experimentalist, this is impossible, right? This is too accurate. You know, the fluctuations of the DACs and just even if you have some super awesome Microsoft DACs, like, I don't know, some $1 million DACs that you built, you still, you know, you don't trust this number for all kinds of reasons, right? You know, even if you took care perfectly of your electrical circuit, then in your device on this scale in a semiconductor with electric fields, if things change on such a scale, it's not meaningful. It's not meaningful. So we see kind of extreme fine-tuning in the experimental plots as well as in the theoretical plots. Now, maybe to a theorist, this is just a number, right? This is as well as good of a number as if it had just like 1.2 here. Might as well put 1.17175. To a theorist, this could be all the same, right? To some theorists. Right. Okay. So finally, let's look at the full protocol, right? This is, let's see, let's make sure this is a theory or experiment. This is the experiment. Good. This is the experimental data. I believe it corresponds to the same regime, right? So that's nice to look at because it's 1.172 here. So here we see this between 1.171 and 1.172, we have some features here. So what are these features?
Can you scroll a little bit to the left?
Yeah, sorry, I over zoomed here.
Yeah,
I tried to zoom in too far.
So now we have basically also input from looking for the gap. Is this a gapped system or not? And that is in plot A, it's sort of schematically depicted with 4 colors.
So I guess this is the protocol, right? This is some kind of.
I think
you pass data through a script, and the script goes and it produces these orange, yellow, blue, and white colors, right?
Yeah, I suspect so. Yes. Yeah, so I think the dark orange region, the orange regions are the ones that are good, so to say, according to the protocol. And then there is another, let me think.
Yeah, that's right.
I
so
honestly, but I'm sort of trying to work out again why the one with the black line around it is like really good and why the other ones, according to the protocol, why the other ones are not. This is a little bit fuzzy.
The blue and white are gapped, but there's no zero bias peak, so that must be trivial.
Yeah.
Then the orange one has zero bias peaks and has according to the protocol, has a gap. Like we'll talk about that in a second, I hope. And then the yellow has a zero bias peak but has no gap. So
yes.
Well,
yeah, I'm just
maybe topological, maybe not. Maybe it's a boundary, topological boundary. So in any case, this dark region of about 40 pixels here, this little island is. Let me go back to this release. How is it called? The underlying physics required to create a new type of qubit. Well, I believe it's right here. It's these 40 pixels or 30 pixels in this island are the underlying physics required to create a new type of qubit. So we already talked about the phase diagram, right? This is the same gate voltage and magnetic field. And we already talked about the fact that this range is narrow. Now the protocol includes these panels C, D, E, F. So what do we see in these panels?
Yeah, so C and D, I think, is the local conductance at either side. So there you see the zero bias peaks emerging at about whatever 1.3 Tesla or so. So zero bias peaks at either side. which is, the first condition according to the protocol, that you have those two zero bias peaks. And then,
yeah, but let me interrupt you a little bit.
Yep.
They look like they start at very similar fields and keep going. So kudos to the Microsoft team for finding that. However, the onset fields are not identical, I think.
No, not quite.
So there is a dashed white lines,
Yeah.
and panel D, I can see 2 or maybe generously 3 pixels over the zero bias peak. But in panel C, it's 1, 2, 3, 4, couple pixels difference, right? But these pixels are large fields, right? So the field range is actually large, and we don't have that many pixels, but it's tens or hundreds of millitesla difference in the well, probably not hundreds, but tens of millitesla difference in the onset points of the zero bias peaks.
Yeah,
probably.
Also, in general, I find this data not to be the cleanest, especially panel D. There's a lot happening. Lots of states are moving around above 1.5 Tesla. Once the first feature comes down to the middle of the plot, there's a lot of features happening, which I think to me indicates that in this local measurement, there's lots of localized states involved somehow that generate all these features. It's sort of,
Yeah, we can also see that from the phase diagram itself, right?
Yes, this is the same.
This is a lot of parabolas going through crisscrossing, and at the intersection somewhere, they found a very, very small region.
Yeah.
Another thing I want to comment. So yes, in C and D, we see zero bias peaks that stick in magnetic field. That alone can be totally trivial states. It's been demonstrated already back in 2014 in a Nature Nano paper from Grenoble, that there are reasons why trivial peaks can stick to zero bias. And yes, the range seems to be long if we say it's kind of like 1 Tesla. Now, if we change gate, they don't show the gate data here, but we can see from the phase diagram. If we go to 1.75 Tesla and change gate, we will have an extremely narrow range of less than 1 millivolt on the gate, where the peaks are at zero bias. Right? So it's extended at this one gate setting. It's extended in magnetic field, and it exists on 2 sides. Now, what about this E and F? This is the non-local signal, right? So this is where they correlate C and D, the zero bias peaks, with something in the non-local signal. What is this something? What do they correlate with?
Yeah, so this is a suppression of conductance in the center. So that starts already like at low magnetic field. There's no conductance in the middle, and then there's some basically the feature that you see in C and D sort of seems to repeat itself also in E and F in making this range narrow, and then it opens up again. So I think what the claim here is that this is a closure of a bulk gap and a reopening of a bulk gap again after this point of closure, which then would signal the topological phase transition.
Right. So this is a non-local signal, and yes, looks similar at first glance. And what they have claimed in the past is that they could see with this technique the gap closing.
Yeah.
And that's the 2021 paper. So this paper here, which we criticized just yesterday, in fact. And now they see the reopening. Now, reopening is significant because that's what you would want to see for a topological region. Yeah. Okay, so the closing is this part. The closing is this part. So this white region shrinks and some kind of signals move in towards zero bias. And one thing to realize about this technique is it does not seem to give signal at exactly zero bias.
Yep.
So some kind of source drain voltage, which is the vertical axis here, is required. It's required to have the signal. You need some source drain bias. And so that creates a stripe with no signal around zero bias. So exactly where the zero bias peak is, in fact. So on the left, we have a zero bias peak here, the yellow bright, which is about plus minus 10 to 15 microvolts. On the vertical axis, now in the exact same range here, 10 to 15 microvolts, we don't see anything. So what we see is the signal approaching it, and then they say, oh, and then it reaches down and sharply goes back up. And it goes back up by, again, to me, by the tiniest amount, the tiniest of the tiniest amounts, from something like 10 or 15 microvolts to something like 20 or 25 microvolts. By 10 microvolts in bias, there is maybe a deflection. I also don't know how they plotted the black line because there is some signal beyond it, but I would hope they applied some kind of a criterion. But this criterion also gives this kind of anomaly, a little spike. Of course, you probably want to just kind of draw something here. Another interesting thing, Vincent, that I noticed here is, if we go back to the old paper, which says defeatedly that they only saw the closing of the gap, unfortunately, no reopening. Well, you know what? If you just look at their data, man. This is 200 microvolts, right? So 10 times more, 200 microvolts. So yes, we see the closing of the gap. Well, I don't know. We can probably find like a 20 microvolt gap here easily.
Yeah.
So, and a zero bias peak.
Yeah.
Here and here, inside the 20 microvolt gap. So
well, did they
discovery
simply
was actually made a year ago.
Did they simply miss it?
I think I think they may have missed it. We made the discovery now here. We made the discovery that was discovered a year ago. Right. So jokes aside, we don't believe that this technique is capable of unambiguously identifying a bulk gap in a nanowire. And that's because this wire is extremely disordered all throughout the wire. Like you can't assume a 60,000 mobility throughout and say that there is some waves that bounce from left to right, and then those waves become gapped by interaction with superconductors, and apply all these models. You just can't. It's very likely much more disordered. There's all kinds of mechanisms by which non-local signal, a tiny signal, by the way, the signal itself is tiny, right? It's 0.05.
Yep.
Whereas here it's 0.8. So it's like 20 times lower signal in a non-local than in a local. There's many ways a tiny signal can get from one side of the wire to the other, find its way and carry some information about all the states that are in between. And so we don't think there is gap there. We don't think there is bulk to talk about, not bulk in the Majorana sense, right? So let's go back to these first figures. This is a wave function, right? Like there's nothing in between. There is one peak on the left, one peak on the right. That's what they think they found, but we think there's so many peaks in between. And there is no topological region in this sense of a pure theoretical vision of a clean parabola and nothing else. That's very unlikely without a lot of studies, a lot of proof in large range, normal range of gate voltages, etc. I wanted to look at one more device. So that's actually the same device, but a different region. So around 1.4, which already tells you.
Yeah, that's like significantly different.
From 1.7, we went to 1.4. So it's been retuned quite a bit, right? By 300
significant,
millivolts.
Yeah.
And we don't see any of that data, right? We see only sort of the 10 millivolts, 20 millivolts zoom-ins on the gate in a large range. So even from this device, we don't see much data. There is a lot more data that they took for sure, probably gigabytes, maybe 10 gigabytes, and we only see a couple of pictures. But here, well, I suppose the point of this figure is that they've done it again and they've saw it again in another spot. The algorithm, the topological gap protocol gave a positive signal. So what do we think about this region?
Yeah, my first impression when I look at this is like messy, very disordered. So many states are moving around in all the data sets. Basically, you can see them. I think these are all the same states. Plot B, but also panel C, D, E, F. This is a zoo of low energy excitations living within this. Definitely, there's proximity-induced superconductivity in these devices. There's no doubt about that. We know that. So in this gap that you have, there's just a zoo of low energy excitations that are sensitive to anything in the sense gates, magnetic field. They wiggle around, move around as you vary. I'm not surprised that if you measure a lot, fine-tune a lot, of course you will find coincidences of zero bias peaks. This is not a surprise.
So your view is that what we see here is an Andreev bound state on the left, Andreev bound state on the right, maybe one more in the middle to like close the gap.
Yeah, look, it doesn't really make point to say how many there are. There's probably, from the looks of it, there's tens, I suspect. Tens of
not hundreds.
Tens of, I suspect this is tens of small puddles, localized puddles of electrons sort of living underneath the superconducting contact, getting an Andreev character, generating Andreev bound states. And there's this whole chain, this cascade, complex network, if you wish, of Andreev bound states living underneath the superconductor. To me, that is a very natural and intuitive explanation for this type of data. Requires to have a somewhat disordered material system or device. Yeah, I don't see, why this. To me, this would be the natural explanation for all these data. And like I said earlier, that the model then manages to assign a topological phase to such regions in the model data. That is also not a surprise, I think. Because it's also an extremely fine-tuned model. So of course you will find some topological phases in the model as well here and there.
Well, the model seems to be looking for a certain pattern, which is captured by C, D, E, F in this figure as well. And as soon as it identifies this pattern, it gives a positive signal, and they produce panel A with these orange colors. So your points are well taken, Vincent. If we go through the features of this figure, we see some of the same behavior, but some of the things are more dramatic. So first of all, the gate voltage range is again very narrow, right? This entire thing is within 2 millivolts, this orange blob, and it seems to be at the crossings of multiple lines in this diagram again, right? So it doesn't seem to be a region like a parabola that we see on the left and on the right. It's crossing of some shapes. I also looked at C and D where we have zero bias peaks. I think more obviously different zero bias peak ranges on the left and on the right, right? So zero bias peak appears at different fields on the left and on the right, and disappears also at different fields. So you can see that the white dashed lines are the same in panel C and panel D, and they mark, I think they mark the area where the two coincide.
Yeah, that's the dashed line.
And then there's also peaks outside that kind of don't coincide.
Yeah.
Right, so it marks this tall peak on the right, I think, is the white dashed lines. And here we have a tall peak outside of the dashed lines. It seems to be a continuously evolving zero bias peak here, but not part of the protocol, I suppose. And here in the black dashed lines, yes, the black gap lines are splitting on the left and on the right, but we already talked about the nature of the signal, how it's very far from being conclusive on being any kind of bulk gap. So really, when I look at C and D, when I just look at it, what I see is two states that cross, maybe stick a little bit around zero, and then other states around them moving. This is a picture I'm familiar with from doing this kind of research, and it's a picture of trivial Andreev bound states on the left and on the right. And if you have a lot of them, you can find them at the same gate setting on the left and on the right.
What else would we like to discuss about it? I think we covered most of what we wanted to say, Sergey. What do you think?
I think so too.
Yeah. So maybe we should allow for some.
Maybe we
summarize, or shall we see if there's questions at the moment? Let people ask some questions. What do you want to do?
Well, yeah, if there's questions, now is the time to post them if something that we said raised concerns or questions or thoughts.
Yeah.
But in the meantime, we can, I suppose, we can summarize. So I can say that I disagree strongly that new physics underlying qubits has been demonstrated in this paper. I think what's been demonstrated is a protocol has been applied, and by allowing infinite fine-tuning, both on the theory and on the experimental side, the protocol has yielded positive signal. The signal is fully consistent from what we see with not having discovered any Majorana or topological superconductivity here. At the same time, the amount of data is extremely narrow, very small amount of data. The ranges are narrowed down, and especially in the gate. There is a second device shown in the paper, but I don't think more. So they must have studied more devices, must have taken more data, but not included it in the paper. And this has been a problem in their past papers, that they don't show enough data. However, think about it, it's unlikely that by looking at more data, we will find more evidence of Majorana here. We will probably find more evidence of no Majorana here if we see more data. Well, unless they overlooked an actual Majorana, by applying their protocol, we will probably not find a Majorana here. We will find further confirmation of what we talked about.
Yeah, so from my end, I concur, of course, with Sergey. I'm just left with many questions. I feel that the reporting is marginal, like truly marginal in terms of fabrication details, device quality, basic characterization measurements. You just you can't really tell much. But given the established understanding that there is in the field about disorders in these devices, I am actually suspicious that these are very fairly disordered devices. And like Sergey says, I'm a bit disappointed, frankly. I thought we would actually get better quality data than this. I have seen better data from other groups in other systems. Why not apply the protocol to those devices? I'm thinking. I'm not, quite frankly, I'm not really following.
Yeah, well, I mean, I don't also believe that this protocol can work, because I don't believe that the non-local signal shows the gap opening. But I mean, the general concept, yes, if you had a measurement that you could actually trust to demonstrate the bulk gap, and you could actually have some reasons to believe that there is a bulk in the system, not just a bunch of localized wave functions all around, then yes, why not? Why not come up with a protocol along these lines. In fact, we also had something similar already a year ago, where we put forward a list of these 5 criteria based all on zero bias peaks alone, no gap involved here. And one reason why we did not include gap was we did not believe that the gap could be established robustly, and we still don't. But yeah, just based on zero bias peaks, think back to this parabolic phase diagram. If we could see it on the left and on the right, just that alone on the 2 sides would be quite interesting to study. We don't see it here. Well, we do see it in the simulation in this paper, but we don't see it in the experiment.
And perhaps a final comment, like I said it at the beginning, there's no qubits in this paper, but if I look at this data, I don't really see how this can ever lead in the current state to any qubits, frankly, or braiding, whatever you want to call it. Like, I would suspect, unless I'm totally missing something here, and there's lots of extra data that contradicts the picture that we sketched, which I honestly highly doubt, then I don't know. There's a long road ahead to go from here to a really clean ballistic system, quasi-ballistic, where you do have well-established topological phases, and that's a prerequisite before you can do any, braiding type protocols or qubits, if you wish. So yeah,
agree. So maybe the conclusion should be that the title of the paper should be something like trivial Andreev bound states passing the topological gap protocol. What do you think?
Sorry, I was distracted reading the chat. Can you
Every time
it?
I make a joke, you are not paying attention. What kind of a friend you are?
Yeah, Wyatt is asking a question.
Okay.
Yeah, this is an interesting question that I wondered about as well. Like, what was first? Was it the protocol? Was there first experimental data, and afterwards the protocol was applied? Like these sort of questions. Like, what loop did they go through? How did these regions get identified as as being, topological or whatever? The paper is written in a spirit that the protocol is a robust way of taking out human biases, I think. Like, that is the spirit.
Like we tried to write papers based on looking at the data, and then they got retracted. So now we're going to do it differently. We're going to collect a bunch of data, send it to the script, like CERN style, right? Where they're going to blind the data. In a sense, experimentalist is only needed to put the thing in the fridge and wire it up, and then push the button, take all the gate and field data,
and then
send it to the protocol supercomputer. The protocol runs and finds a region. Then they look and say, "Oh, there's zero bias peaks on 2 sides. Okay, it's there."
Yeah.
Right. That's my guess. It's just a speculation, but it's kind of my guess.
That's pretty much it.
Somebody confirms.
Yeah. Yeah. All right.
Well, I guess that's one way of doing things, but okay. Once you sort of unblinded the data, you could do a couple of sanity checks, like look at the gate range and see that you're talking about microvolts on the gate, these kind of sanity checks. All right, it's been a while. It's like 1 hour, 15 minutes, longer than I thought we would take. I apologize for talking so much, but it's probably time to stop. the recording. Thanks to those who actually connected on a very short notice. Thank you very much. We will post this recording, and please spread it to people who might be interested. It's a super long, boring discussion of one paper, but some people might actually find it relevant. So I'm going to stop the recording now. And thanks, everyone.
Yeah, thank you very much. We might do a right